Hello everybody, this is lesson 15. This is kind of related to lesson 14. In fact, it's very related to lesson 14. Basically, we are going to take everything that we learned with lesson 14 and apply them to word problems. I know that for a lot of us, word problems can be confusing and dense and a little bit overwhelming, and I understand that. But hopefully by the end of this, you'll feel a little bit less overwhelmed. So in order to solve these what we call applications, that's just a fancy name for word problems, using this linear programming, this is what we do. We first write down our question of interest. Is this a maximization problem or a minimization problem? Then I define my variables to answer my question of interest. For the sake of simplicity, we call these x and y. Then I write down the objective function to answer our question of interest. I list any constraints given in the problem, and then from there we're golden, because we just graph the constraints, shade the feasible region, identify the critical points, and then use our critical points and objective function to find our max or min. All of these last four steps we did in lesson 14. So let's look at our first example. We have, at a university, Professor Simons wishes to employ two people, John and Mary, to grade papers for his classes. John is a graduate student and can grade 20 papers per hour. John earns $15 per hour for grading papers. Mary is a postdoctoral associate and can grade 30 papers per hour. She earns $25 per hour for grading papers. Each must be employed at least 1 hour a week to justify their employment. If Professor Simons has at least 110 papers to be graded each week, how many hours per week should he employ each person to minimize the cost? So yeah, there's a lot of information here, right? But we are going to parse through all of this information just fine. First step is to write down my question of interest. So it gives it to us. How many hours per week should he employ each person to minimize the cost? So how many hours should John and Mary each work to minimize grading cost? This is the question that we want to answer. We are minimizing cost. Next, I want to define my variables to answer my question of interest. So I'm going to call x the number of hours that John works. And I'll call y the number of hours Mary works. Step 3 is to write the objective function to answer our question of interest. So remember, we want to minimize our grading cost. So I'm going to call this function c for cost, c of x, y. And my total cost is the number of hours that John works, that's x, times how much John is paid per hour, that's 15. So this 15x represents how much John is paid. And then I have Mary, who works y hours, and for every hour she works, she gets $25. So this one is Mary, how much Mary is paid. This is the function that we wanted to minimize. Now I will list any constraints given in the problem. So I have a couple constraints. I first have that each must be employed at least 1 hour per week. So this tells me that the number of hours that John works, x, has to be greater than or equal to 1, and the number of hours that Mary works, y, also has to be greater than or equal to 1. I also have if Professor Simons has at least 110 papers to be graded each week. So I have at least 110 papers to be graded each week. And I know that if John works a number of hours, he can grade 20 papers per hour. And if Mary works a certain number of hours, she can grade 30 papers per hour. So this equation is papers graded, which looks a little similar to our objective function. So it's important that we keep these straight. All right, now we are on to our next step, graphing the constraints and shading the feasible region. Oh, excuse me. So I first will graph this guy, x is greater than or equal to 1. So here is the line, x equals 1. And I want to be greater than or equal to that. So I will graph to the right. Okay. And my other one, we have y is greater than or equal to 1. Oh, let me do this one in green, actually. So we have y is greater than or equal to 1. That is this one right here. And since I want to be above this, I will graph above it. All this right here. So far, my feasible region is this square in the upper right corner. Then I have this equation that I want to solve. So my equation is 110 is less than or equal to 20x plus 30y. So let's solve this for y. If I subtract 20x over to the other side, I get 110 minus 20x is less than or equal to 30y. Then I will divide by 30. This gives me 11/3 minus 2/3 x is less than or equal to y. Now, because of these fractions, it would be a little bit tricky to graph this using our slope and our y-intercept. So instead, I will make a table. Let's first see, since I have the line x equals 1 on here, let's see what happens when I plug in x equals 1. This gives me y equals 11/3 minus 2/3, which is equal to 3. So I have the point 1, 3 right there. And then 3 over will be 4. So when I plug in x equals 4, I get y equals 11/3 minus 2/3 times 4, which is equal to 1. So I have this guy right here. So this line looks something like this. And next, I want to figure out which region I should shade. So I will plug in a point 0, 0. This gives me 11/3 minus 2/3 x is less than or equal to y. If I plug in 0, 0, I get 11/3 is less than or equal to 0, which is not true. So I want to shade in the region that does not contain our point 0, 0. So that's going to be all of this up here. So I can see that my feasible region, now that I have graphed all of my constraints, my feasible region is this guy right here. So I go forever up and forever out. My only two critical points are this guy and this guy. And in this case, they're pretty easy to find. My first one is actually the first point that I plugged in. And I know that it's that point since I'm on this red line, which is the graph of x equals 1. So my first point is, critical point is 1, 3. And my second critical point is on the line y equals 1. So I know that that is also this guy. So my two critical points, in this case, it was pretty easy to find them based on looking at the graph. In some cases, we'll have to do a little bit more algebra in order to find them. Now I want to use these critical points and the objective function to find the max or and then value. So remember, my objective function was c of xy equals 15x plus 25y. And I want to minimize. So I'm going to plug in both of my critical points to see which one gives me the minimum value. So c of my first one, 1, 3, will be 15 times 1 plus 25 times 3, which is 15 plus 75, or 90. Next, I have c of 4, 1 is equal to 15 times 4 plus 25 times 1, which is 60 plus 25, or 85. And since I want to minimize, I see that 85 is clearly smaller than 90. So the 0.41 is what I want. So I have, this is my x value, and 1 is my y value. So what does this mean? Well, this means that to minimize the grading cost, X was my number of hours that John works, so John should work 4 hours. And Mary should work 1 hour. Pretty cool, right? We parsed through all that information and we found our solution. All right, let's go on to another example. We have Hamer is on a low cholesterol diet. During lunch at his work's cafeteria, he always chooses between 2 meals, pasta or tofu. The table below lists the amount of protein and vitamins each meal provides, along with the amount of cholesterol. Hamer needs at least 200 grams of protein and 40 grams of vitamins for lunch each month. Over this time period, how many days should Hamer eat the tofu so that he gets the adequate amount of protein and vitamins, at the same time minimizing his cholesterol intake? So my question here is, how many times should Hamer eat tofu? I personally love tofu. I actually had tofu for dinner tonight. How many times should Hamer eat tofu? To minimize the cholesterol consumed. Okay, now I have variables to define. So I'm either going to eat pasta or tofu every day. So those are my 2 variables. I'm going to call x the number of times I eat pasta. And I'm going to call y the number of times I eat tofu. Next, I want to write down the objective function to answer my question of interest. Again, I want to minimize the cholesterol consumed. I'm going to call this C for cholesterol of x, y. So the amount of cholesterol I consume, sorry about that, is the number of times I eat pasta times that amount of cholesterol, which is 60, plus the amount of times I eat tofu, that's y, times that amount of cholesterol. And this is what I want to minimize. Now I want to list any constraints given in the problem. Well, I have a few. I need at least 200 grams of protein and 40 grams of vitamins. So let's write an equation for protein. And vitamins. Oh, wow, I'm having trouble spelling. Vitamins. So the amount of protein that I get has to be at least 200. And then the amount of protein I get is how many times I eat pasta. Well, pasta has 8 grams of protein, plus the number of times I eat tofu, plus the number of times I eat tofu times the amount of tofu that that has. For vitamins, I need at least 40 grams. And that will be the amount of times I eat pasta times 2, since that's how many vitamins are in the pasta, plus the amount of times I eat tofu times 2. And then I have one more constraint. I am trying to find this over each month. So the number of times I eat pasta plus the number of times I eat tofu cannot be more than 31, since 31 is the maximum number of days in a month. So month-wise, since all of this is over a month, I need x plus y is less than or equal to 31. The number of times I ate pasta plus the number of times I ate tofu won't be more than 31. Depending on the month, of course, but we'll call it 31. All right. Now I want to graph my constraints and shade the feasible region. Well, I can do that. So let's graph my protein first. So I have 200 less than or equal to 8x plus 16y. To solve for y, I'm first going to subtract 8x from both sides, which gives me negative 8x plus 200 less than or equal to 16y. And then if I divide by 16, I get negative 1/2 x. 200 divided by 16 is 200 divided by 16 is 12.5. So I have 1/2 x plus 12.5 is less than or equal to 1. So let's plug in some points here. Let's see what happens if I have x equals 3, for example. This gives me y equals negative 1/2 times 3 plus 12.5, which is equal to 11. So I have the point 311, which is just one above my graph. And then let's say I have the point 7. That gives me y equals negative 1/2 times 7 plus 12.5. That is equal to negative 3.5 plus 12.5, which is equal to 9. So I have the point 7, 1, 2, 3, 4, 5, 6, 7, 9. So my first, this blue one, will look something like this. That's for protein. Next, I have my vitamins. Oh, actually, I need to shade my region, don't I? So I need to test my region to see which one I need to shade. So let's plug in a point. 0, 0. So this would give me 12.5 is less than or equal to 0, which is not true. So the point 0, 0 is not included in my region. So I need to shade the region that does not include the point 0, 0. So that'll be this guy up here. All right, that's my first equation. I'm going to erase all this so that we have room for the other one. So now I have vitamins that I have to deal with. So if I look at this one, I have 40 less than or equal to 2x plus 2y. Solving for y, I first subtract 2x to the other side to get 40 minus 2x less than or equal to 2y. And then I divide both sides by 2 to get 20 minus x is less than or equal to y. Okay, so let's plug in some points here. If I plug in the point, let's see. If I plug in 10, this gives me y equals 20 minus 10, which is 10. So I have the point 10, 10, which is right here. And then let's plug in 8. So that gives me y equals 20 minus 8, which is 12. So somewhere over here. So this graph looks something like this. So over in this direction, they're not going to intersect. They're getting further away from each other, but they will intersect in this direction. Next, I need to figure out my shaded region. So let's plug in the point 0, 0. If I do that, I get 20 less than or equal to 0. Not true. So I shade the region that does not include the point 0, 0. which will be this guy. Okay, I have one last constraint, my month constraint. So I have x, oh, you know what, let's do this in green. X plus y less than or equal to 31, which gives me y is less than or equal to negative x plus 31. So my my graph is gonna this graph is not a great scale. So obviously my y-intercept is gonna be like way up here, and then my graph my slope will be negative x. So it'll be something like this. That's just a rough estimate. So then let's see what my shaded region here should be. If I plug in the point 0, 0, I get 0 is less than or equal to 31. Not true, obviously. So let's shade in my region, which would be this guy over here. So we can see that my two critical points are when my green intersects with my red. Oops. So right here, when my green intersects with my red, and when my red and blue intersect with each other. So I need to identify my critical points. So if I intersect between the green and the red, this gives me, well, my green one is negative x plus 31. I set them equal to each other. My red one was vitamins, which was negative x plus 20. Oh, sorry, these don't actually intersect today. Sorry about that. It just, the way that I drew the graph looks like it does. So this graph is a little bit rough, but if I were to, so let's find this critical point right here. So that is where the red and the blue intersect. They will eventually intersect. So my red one was protein, which was negative 12, oh, sorry, positive 12.5 minus 1/2 x. And then my other one was 20 minus x. So let's solve for this guy. If I add 1/2 x to both sides and subtract 20, I get 12.5 minus 20 is equal to negative 7.5 is equal to x minus 1/2 x is equal to positive 1/2 x. So if I divide both sides by 1/2, let's see. Sorry, I'm going to pause this real quick. All right, so I have just pulled it up onto Desmos. Hopefully this will make it a little bit easier to see. So I pulled up all of these graphs on Desmos. That way it's a lot easier to find our intersection. That graph was not helping us out at all. So I see that I have a couple of critical points. Remember that our x represents the number of times I ate pasta, y represents the number of times I ate tofu. In this case, it doesn't make sense for either x or y to be negative. So that means that I have critical points on my, I will have a critical point right here. The only critical point I have is at the point 31, 0. Remember, my shaded region was all of this up here. Actually, I think I can make this shaded. Whoops. I want this guy, I want this guy, and I want this guy. So we can see here that this region right here is my feasible region, right? So here my only critical points are 0, 31 and 31, 0. This graph makes it a lot easier. So I have 0, 31 and 31, 0. Those are my only critical points. So let's test each of these critical points. So my critical points are 0, 31 and 31, 0. 0, 31 and 31, 0. And my objective function was c of xy equals 60x plus 50y, and I wanted to minimize this. So c of 0, 31 will be 0 plus 50 times 31, and 50 times 31 is equal to 1550. C of 31, 0 is equal to 60 times 31 plus 0, and 60 times 31 is equal to 1860. So clearly my minimum value here is 1550. So that gives me the point 0, 31. And remember, x was the number of pasta meals, and y was the number of tofu meals. So this means that to minimize cholesterol, and to get all of the nutrients that he needs, proteins and vitamins, really, he should eat tofu every day. It's kind of boring, if you ask me. I would mix it up, but you know, maybe he's pretty serious about his cholesterol. Homer should eat tofu every day. So sorry about that graph malfunction. This graph was not not great since the scale was off, but hopefully that worked in Desmos just fine. So that is it for today. Let me know if you have any questions on this, or come to the Zoom meeting if you'd like me to do some more examples. Hopefully I will see you there.